Alright, today we're diving into two puzzles that just completely break the rules of normal computers. I mean, imagine this finding one name in the list of a billion, almost instantly, or cracking a code that should take a normal computer longer than the entire age of the universe to solve. The keys of pulling off these seemingly impossible feats are hidden in the very strange and wonderful world of quantum computing. So let's start with our first puzzle. Picture a massive disorganized phone book, and when I say massive, I mean it has a billion names. With a normal computer, your only option is to start at page 1 and just grind your way through checking every single entry. In the worst case scenario, that's a billion checks. It's brute force. But what if I told you a quantum computer could nail it in the time it takes that same regular computer to check just 30,000? How is that even possible? And for our second puzzle, while the stakes get way higher, we're talking about modern encryption. You know, the very foundation of all of our online security. The digital locks that prevent and protect your emails, your bank account, and everything from basically being stolen. They're designed to be so incredibly tough that a classical computer would need billions and billions of years to break them. So, how could a quantum computer possibly pick that lock? So where do the answers come from? It's not just building a faster version of computers we already have. They come from a very completely different kind of mind-bending way of thinking about computation itself. The solutions are two of the most legendary algorithms in history, Grover's algorithm and Shor's algorithm. So let's dive into that first puzzle, finding a needle in a haystack, or if you want to use the computer science term, unstructured search. Now, to really get our heads around the quantum approach, we need to find a new way to think about the problem itself. To do this, we're going to use something called the query model. Just imagine that our database with a million names is locked away inside of a black box. We can call it an oracle. You can't see into it, you can just pop it open and browse. Or at least you can't. The only thing you can do is to ask very specific yes or no questions, what we call queries. So you can ask, is the name in here John Smith? And the oracle will just say yes or no. That's it. So the name of the game is defined by the right person asking the fewest questions possible. That's how we measure just how efficient we are. The quantum key that unlocks the search puzzle is an algorithm that was developed by Love Grover. And what's so cool about it is that it doesn't find the answer by checking one name, throwing it out, checking the next, and so on. It does something much, much cleverer. And this right here is the core engine, the Grover iteration. First, it kicks things off with a wild quantum trick called superposition. This means the computer is considering every single name on the list at the exact same time. Yeah, all 1 billion possibilities exist at once, each with a tiny, tiny chance of being the right one. Then you ask the oracle just one question: is the answer I'm looking for in here? The oracle doesn't tell you what the answer is, but it secretly marks the correct one. Think of it like it's putting a tiny little invisible flag on it that only the quantum computer can see. And then comes the final magical step, amplification. The algorithm runs an operation that hugely boosts the probability of the marked answer while at the same time lowering the probability of all the others. And then you just repeat the cycle, mark, amplify, mark, amplify. This is a perfect way to picture what's happening. With every single cycle of the algorithm, the probability of measuring the correct answer just gets higher and higher, while the chance of getting any of the wrong answers smaller and smaller. You're basically making the needle brighter. Now you might be thinking, I'll just keep amplifying forever until I'm 100% certain to get the right answer. But not so fast. There's actually a little catch, kind of like the Goldilocks problem. As this quote points out, the probability actually oscillates. If you run the amplification step too many times, you completely overshoot the target and the chance of finding the correct answer, which starts to go back down again. You'll have to stop at just the right moment to have the best chance of success. So how do you know when to stop? Well, the math is beautiful. It shows that the perfect number of steps is roughly the square root of the total number of items, which we will call n. And that's what this formula on the screen is all about. For a billion items, the square root is around 31,600. So while a classical computer could need up to a billion guesses, Grover's algorithm needs only about 30,000 queries. This isn't an exponential speedup, but it's a massive game-changing quadratic speedup. Okay, let's switch gears and move to our second puzzle, which honestly is in a whole different league. Modern encryption, the stuff that keeps us safe online, relies on a really simple fact. It's super easy to multiply two huge prime numbers together, but it's practically impossible for a classical computer to take that resulting giant number and figure out what the original two primes were. This is the factoring problem, and this brings us to a really crucial distinction between our two quantum keys. Grover's algorithm, as we saw, is a search tool. It finds a specific item and gives us that powerful quadratic speedup. But Shor's algorithm, it does something fundamentally different. It doesn't look for an item, it finds a hidden pattern. And that single ability unlocks a frankly terrifyingly powerful exponential speedup, the kind of speed that can shatter modern cryptography. So how on earth does it work? Well, the genius of Peter Shor's algorithm is that it doesn't even try to attack the factoring problem head on. As the source says, it reduces it to a completely different but related problem called order finding. If you can solve order finding, you can solve factoring. It's an incredibly clever end run around the original problem. So what in the world is order finding? Well, you can think of it as like finding the length of a repeating pattern in a strip of wallpaper. We'll call that n. And then you just pick some random number, a. The whole goal is to find the order, which we will call R. That's the smallest power you need to raise A to. So that's when you divide the whole thing by n. You're left with the remainder of 1. This R value is the key. It reveals the length of a hidden mathematical rhythm. This table makes it really clear with a simple example. Let's factor the number 21. We'll just randomly pick the number 2 to be our A. As we calculate the powers of 2, we'll look at the remainder after dividing by 21. So the sequence of the remainders goes 2, 4, 8, 16, 11, and then boom. At 2 to the power of 6, the remainder is 1. We found the pattern. The order R is 6. Now look, finding this for the number 21 is easy, but finding it for a number with hundreds of digits is classically impossible. But it's exactly what quantum computers are born to do. The special quantum tool that does this heavy lifting is called phase estimation. You can think of it like a super advanced musical tuner. But instead of listening for the pitch of a sound wave, it's listening for the frequency of this hidden mathematical pattern. It's uniquely designed to find that repeating period R with astonishing mind-boggling speed. So this is really important to get. The whole thing is just a hybrid process. It's a team of effort. The quantum computer does the ridiculously hard part. It runs phase estimation to find order R. The number then gets handed off to a regular classical computer, which uses some pretty simple math with that R to calculate one of the factors of n. And what's remarkable is that each time you run this whole process, you have at least a 50% chance of finding a factor. So you just run it a few times and success is practically guaranteed. Okay, so we've seen how these two incredible algorithms solve these incredibly difficult problems, but their real importance, their lasting legacy. It goes way beyond just searching databases or factoring numbers. Let's take Grover's algorithm. It's a core technique. This amplification is now a fundamental tool. It's used as a kind of booster shot in all sorts of other quantum algorithms. And here's the kicker. It's been mathematically proven to be asymptomatically optimal. That's a fancy way of saying that for this kind of search problem, it's the fastest it can possibly be. You literally cannot design a quantum algorithm that does it better, as far as we know, of course. So when you boil it all down, the true legacy of both Grover's and Shor's isn't just about the specific problems they solved. It's that they gave us the foundational techniques, things like amplitude amplification and phase estimation, that have become the essential building blocks for countless other quantum algorithms. They gave us a whole new toolkit for how to think about computation. And that brings us to a final and pretty thrilling thought. Grover's and Shor's gave us these absolutely mind-bending solutions to problems we already knew existed. The real question, the exciting question, is what future puzzles that we can't even imagine today in medicine, in material science, in AI, what will these fundamental quantum tools unlock for the next generation? I hope you enjoyed this episode of Quantlock, and I hope you all have a great day.